So I think everyone's aware of what we're talking about today, detecting deepfakes. So I'll just get right into it. So just a little bit about myself. I did a bachelor's in business entrepreneurship. I went to Arizona State. Many of you are familiar with that. Um, and I went through thinking that I was going to start the next like Facebook scale business and I was going to do all these amazing things. And then I got to the end of the program and I realized I didn't have the money to start a business like that. I didn't have the skills to necessarily program something out myself. And so I was running a business where I was basically reselling computer components. And eventually I just realized that wasn't really what I wanted. And I also saw how interesting machine learning and programming and all of that stuff was. And so I started pivoting and I started building little tools for my own business in order to utilize machine learning and boost what I could do. And so I just kind of self-taught with whatever I needed. I just picked up the skills from YouTube videos and random tutorials. And eventually, when my business was starting to just fall apart because I was spending too much time doing machine learning and not enough time running the business, I started looking for a job. And so my problem was I didn't have any degree saying I could do CS. I didn't have any professional experience doing it. Um, so what I found was I can do these Kaggle competitions. Maybe if I do really well, maybe that'll be a little ribbon in my hat or feather in my hat that can be used as bargaining so I can get a job. And so I tried on my own. I said, I've done these online courses. I think I could do pretty good at these. I did a first attempt, just could not make any progress, wasn't beating the public kernels, couldn't do anything on my own. And so what I did is I went to one of our local meetups and I was looking for other people to team up with, possibly get me over that hump and help me build my skills. And I got super lucky because the first time I went there, I met this guy, Alex, who was an ex Microsoft employee. He was trying to find a new job and he was trying to build up his machine learning knowledge. And so both of us, basically unemployed, spent the whole 3 months working on this competition, just building up our skills. And so that's the top competition on my profile, the one that we got third on. We just spent basically every waking moment working on that competition. And so that was my first interaction with kind of community and machine learning, and I really enjoyed that experience. And so the original meetup that I was going to eventually fell apart, and so I started up the San Diego Machine Learning Meetup and kind of built that out, trying to replicate what an experience that had been for me, where I got to meet other motivated people and build up my skills. Um, so the rest of the stuff you can see on my Kaggle profile. I'm pretty active on there. I basically every day I spend at least an hour or two looking at that stuff. And yeah, that's it for me. Um, and so looking at deepfakes, I think probably most of you are familiar with deepfakes, but for those of you who aren't, deepfakes are these videos that have been altered in some way. And I'll just play this for you guys. I don't know if you'll have audio. It's not really material to have the audio. The biggest thing is that you can see that there's a face that has been swapped here. Um, and so you can see from that, that's a deep fake. Basically, you've got Jennifer Lawrence. Lost my mouse. There we go. Um, you can see it's Jennifer Lawrence swapped faces with Steve Buscemi. And it doesn't look very natural here because it's such a jarring difference. But that's generally what we're talking about, is some video manipulation method that can put someone's face on top of someone else's, and then if you combine it with other technologies, you might be able to swap out voices as well and make them say something else. Um, So just to informally define what a deepfake is, it's a video manipulation technique that generates a face and puts it somewhere else, basically. And the reason it's called a deepfake is because it uses a deep neural network. And so the deep is the deep neural network, and then the fake is just, it's a fake face. Um, and so why would we want to detect deepfakes? There's lots of malicious ways that you can um, use these, and one of the major ones is revenge porn. And I know that that's kind of a taboo topic, but it's important to bring it up because the original deepfake library that popped up, its most prevalent use was actually for porn, and it was so ubiquitous for that that it was actually originally posted on a subreddit, and that entire subreddit got nuked because it was just only being used for that, basically. And so eventually it got removed from Reddit. So it's important to understand. A lot of people talk about it for political manipulation and stuff like that, where you might be able to make some world leader say some ridiculous thing. But it is very heavily used in the porn setting. That's where the big money is, really. So it's important to understand that that is one of the primary uses of it. And another one is evidence tampering. So you might be accused of some crime, and you say, no, I didn't do that. And they go, oh, we have this video of you walking into this place and shooting this person or something like that. And with a very successful deepfake, you could just build a video and say, yeah, here's you doing it. And you don't really have a way to fight against that. And so bottom right corner here, this is actually a deep fake. You wouldn't expect it, but it's a pretty good recreation of Obama, and you can alter his face with someone else's who's talking and saying something and just doing an impression of him, and it will actually stitch on top of his face. And then the other thing is Microsoft and Facebook and Amazon Web Services teamed up, and they set up $1 million challenge for this. So it's important to it's just a high dollar thing, so you might be interested in it for the money. I see there's some chat. Are there any questions here? More about the San Diego meetup.
Sorry, Ryan, can you see the chat messages? There are a couple of questions.
Yeah, I just pulled them up. Yeah.
Okay.
Yeah. So regarding the San Diego meetup, we typically do it as an in-person like you guys do, and we have two separate sessions. One of them is a book club. Right now we're reading Hands-on Machine Learning with Scikit and TensorFlow and Keras, and we're pretty far along with that. We do about a chapter a week, and we get together and we discuss and we just kind of learn together. And then the second session, we typically try to get together. And recently, we've been doing community projects regarding COVID-19 and stuff like that. But our typical would be looking at Kaggle competition. So we get people together and we try to brainstorm about these things and just see how we can compete together. Right now, it's remote, though. So if you guys want to join in on either of those, you're welcome to.
So actually, I have a further question on that. So like, how does that typically work? Do you try to get groups spawned like from within the meetup to organize within themselves and compete, or is it like a meeting place for like the whole group works on a competition together?
It's pretty loose and fluid. I think we have similar problems that you guys had where people come in and they might take some interest and then they might say, oh, I'm going to work on this thing, and then they don't show up next week. So the way we typically run it is we'll just typically I will just lead us working on something. So I'll just work on it for 3 weeks, 4 weeks, or something like that. And then whoever sticks around for a long enough period, then we'll actually form teams. If there's only enough to form one team, then we'll do one team. If there's enough to do two, then we'll split into two. And that's typically how it works. We don't really have, it's not a massive amount of people. It's typically enough to just fit in two teams. And then we also often have people who kind of just want to be observers and learn from the people who are working on this stuff, because they don't feel like they have the skills necessarily to contribute, so they just want to do it as like a learning experience.
Cool. Thanks.
Yeah. There was a question about revenge porn. So the money in that can come from various different ways. It's powerful as a blackmail tool. If you can generate porn of someone and then you can say, if you don't do this, or if you don't give me money, I'm going to release this video of you and make everyone believe that you released a sex tape or something like that. And that is true of world leaders and ex-girlfriends. And I mean, it's just a very powerful blackmail tool potentially. But there's also a big market for, if you want to see some celebrity doing heinous acts, you can just generate that. You don't have to wait for them to actually get naked on camera. And so there's the porn industry is very interested in these technologies. What's the original purpose of deepfakes? I don't know the full history of it, but my understanding is it was kind of just an academic endeavor of proving, can we do this? We'll look at kind of the technology behind it, and it's kind of just an interesting trick that is surprising that it works. Yeah, so we'll look at that in a second. So how it works, there's several different libraries that do deepfakes, and the one that we'll be looking at is the most popular. It's just called Face Swap. It's under the GitHub repo, or the GitHub user deepfake, and then the repo is called Face Swap. And so the way that library works is it's got three different phases, basically. It's got extraction, it's got training, and then it's got conversion. And so extraction is basically, you want to gather a whole bunch of videos of an individual, and you have to gather a whole bunch of videos of another individual, and then you have to extract out their faces from all of those videos in order to get a lot of examples and a lot of data regarding what those faces look like. And so this is fairly simple for a lot of public figures. It might be harder for someone who doesn't have as big of an online presence. So a lot of people have looked at movie stars and Joe Rogan and people who have a lot of video content online, because you can get massive amounts of frames of their face, basically. And so the way this extraction process works is you've got the original video that's 1920 by 1080, and then you use a pre-trained face detector. So there's a bunch of models out there that will basically locate faces within a picture or video. And so you detect where it is, and then you crop into that region, and then you try to flatten it out. So someone might have their head to one angle or another angle, and you want all of your faces to be consistent. So what it will do is it will look at the facial key points. So there's also models, might be combined with the face detector, that will detect, here's the leftmost point of the eyelid, here's the bottom right point of the chin. And so it uses all of that information to then make a bounding box and then do a rotation and transform that will make it so all of them are flat. It will basically extract the information out of the full frame and pull out just the face and flatten it. And so that's important because it makes it consistent across all of the different frames. And so at the end, what it would look like is something like this, where you pulled out just the face of many different video frames. It works better if you have lots of different settings. So this is probably not ideal. If you just have the same face in exactly the same setting and lighting and all of that stuff, then it probably won't get you the best results. But if you just pull a ton of frames out of a ton of different varied videos, you'll probably get pretty good results. And so the next step is, after you've compiled that whole data set with all of the faces of your source and your target, who you want to start with and who you want to transform them into, then you have to do this training process. And what's done in this training process is you use an autoencoder that will compress down the information of the person's face to a very dense representation, and then it will try to reconstruct it. And so looking at how they start, typically the starting resolution would be 256 by 256 by 3. So you start with a 1920 by 1080 video probably, and then you crop out just the face, and then it's just 256 by 256 by 3. And then the encoder will try to compress that down, keeping the most information that it possibly can, and that will be kept in a 128 length vector. And so the way you can think of this is it's trying to capture what that face looks like. And so if we as humans were to try to do that, we might say, oh, they have blonde hair and their mouth was slightly open and they were looking at this angle. And so you might fill out 120 different variables and say, this is the state of all of these different things. And then given a skilled artist, you might be able to tell them all of this stuff and they might be able to draw it given just your verbal explanation of what it is. And so that's similar to this concept of an autoencoder, except for the stuff isn't interpretable. So it's just plopping out a 128 length vector, and that's its description. And then the decoder on the other end is trying to decompress that and actually draw a face given that description, basically. And so the way these deepfakes are done, you have a combined encoder. So both of them are trying to make this vector here, and then you have a separate decoder. So one of them is trying to decode and make Sally, and the other one's trying to make Bob, for example. And so they have this combined language here of the encoder that is compressing them in the same way, but then they're decoding them in a slightly different way. I see some questions popping up. So do these techniques fail when someone's face is turned such that only one eye is visible? They don't entirely fail, but they do become significantly worse. And we'll look at some examples later on. I have some pictures of people who have side-on faces, and then the performance kind of goes haywire. It can infer where things are with the facial key points and stuff like that, though. Do people do this with CycleGAN and follow-on methods? In the approaches that I saw, they typically don't. The more state-of-the-art stuff is using GANs. You might be able to generate, I saw a recent paper that can generate an entire body or an entire video rather than just the face. But the ones that are easily available right now that aren't just research projects, they all just do the face, and they don't use GANs or anything like that. They're just doing autoencoders and then swapping the back end. How does it actually ensure things look decently consistent between frames? That is the trick. It doesn't. It's just looking at individual frames at a time. I'll talk about that a little bit more on a later slide. So what I was talking about before, they've got this common encoder, which is basically compressing it down in some consistent way that's trying to capture the same variables. And then you can swap this decoder onto this section. And then instead of reconstructing face B, it will reconstruct face A, for example. And so that's the general premise of how it generates a new face with the characteristics of a different person. How do they ensure the lane spaces are aligned? So that's the beauty of having the same encoder. So we know that they're sharing the encoder, and that is making it land in the same space. Because if they were entirely separate, then they wouldn't end up. It would be someone describing a face in French and someone describing a face in English, it wouldn't be the same language and you wouldn't be able to reconstruct it. The fact that they're shared is very important, actually. And so then the third step in this library is actually converting. So now we're able to extract the face out, and then we do the transform matrix to make it look flat. And then we take the deep fake, and that will take this face and turn it into this face. And so now we have the new face, but we have to stitch it back onto the old video. So you take that, and then you do the inverse of the transform we originally did to flatten it out, and that will fit it back on the original video. But the next problem is it probably doesn't look seamless. It probably, there's nothing that is constraining the deepfake model to make it look nice on the new frame. So you have to do various different things to kind of smoothen it out. So one of the easy things to do is you just slightly blur the edges. So it just smooths things between the old video and the new face that you've plopped on top of it. And then you can also do histogram equalization, which is looking at the distribution of the colors and making sure that it kind of lines up. So you don't have a generated face that is super bright on a surrounding face that is dark or something like that. And so that helps it look slightly more continuous. And then there are other post-processing steps too. So you might take the facial key points and you say, I only want the point from the top left eyelid to the bottom of the mouth, and you can kind of constrain it with that. So you're altering the minimum area, but still capturing the face difference in some way. And so the details of the actual competition, we had just a massive set of videos. We had over 100,000 videos. They were 10 seconds long. 300 frames typically, some of them give or take, and that ended up being about 500 gigs of 1080p video, and that was MP4 compressed. So it was just a big bear just to deal with downloading that. I think that knocked out most people who were trying to compete. And then we were given the source video, and then they made multiple fakes for every source video. So we were given the real video, and then we were given 5 plus or minus a few fakes of each video with some random face that was kind of swapped on. And one of the details of the competition was it was paid actors. It wasn't organic videos necessarily. It wasn't just random YouTube videos. They had a set of 200 people or so who were just kind of interacting with their friends or answering interview questions or just walking around. And then they just cut that video up into 10-second clips and then gave it all labeled. And most of the fakes are pretty bad. We'll look at a few of those later. They're not nearly as good as the one we looked at before. And the metric is log loss, and that'll be important later for some of the techniques that were used. Were all the fakes just face swaps manipulations? So that's another detail we'll touch on in a second. 8% of the videos had audio manipulation as well, but almost all of them were just face swaps in some way. What's the data cleaning process involved with video images? We'll talk about that in a second too. I talk about my whole pipeline because I think that's actually probably the only valuable thing I got out of this. And so here's an example of one of the bad ones. This poor guy got his face grafted onto someone else. Doesn't look very good. And so I start with just a simple baseline approach that I think most people who have done Kaggle competitions in the past would do, which is basically a video is really just a collection of frames. It's just a bunch of pictures stacked on top of each other. And so what you can do is you can just say, I'm just going to grab a random frame from every video and I'm going to apply a convolutional neural network, and I'm going to train on that. But part of the problem there is that it's still just a massive amount of data. If you just want to pull a single frame from every single video, that's going to take a while. You need to do some pre-processing step in order to make it more accessible, because decoding the MP4s alone, if you did all 100,000, at least on my system, it was taking 10, 12 hours. So if you just want to do one loop through the data, you're going to take 10 hours, which is not really manageable if you want to do multiple epochs of training, or if you want to do repeated experiments. And so one of the other issues with that approach is that not necessarily all of the frames are faked. So it might be the case that it's someone's regular face for the first 5 seconds of the video, and then a new face gets popped on top of theirs. And so if you just pick a random face out of the set, then you might get bad signal because you labeled it as fake, but really that frame you showed the model was actually real. And so on top of that, the 1920 by 1080 resolution is pretty big in terms of computer vision models. Most of the models typically operate on 224 by 224. And so dealing with the data, I kind of broke it up into 2 separate parts, one of them being focus, just making sure that I'm looking at the region that actually matters. So we know that only the facial region has been altered, so you don't necessarily need to look at the rest of the surrounding video in order to determine whether it's a fake or not. And then the second portion of that is actually storing all of this. So like I was talking about, the MP4s take a while just to decode. So you probably want some way so you can decode them once, store it in some easy to use way, and then not have to do it every single time you run through the data. And so in the bottom left, you can see here's an example of what it might look like, where you'd use a face detector and you just find the region where the face is, and then you say, I'm just going to grab the 300 by 300 pixels of this face. And so 2 of the approaches that a lot of people used were just folders and JPEGs. And so basically you're pulling each video and you might make a new folder for that video, and that folder has all 300 JPEGs that represent that video. But the disadvantage of that is you have to manage all of the directories, and it's just a bunch of piles of files, and you have to do all of the bookkeeping related to that. And so one of the advantages is the JPEG compression will make the individual files smaller. It'll still be bigger than the MP4s because the MP4 compression is stronger, but it's going to be smaller than just doing a raw NumPy array. One of the disadvantages is that you still have decoding costs. So if you take a JPEG, you still have to turn it into a NumPy array. And it might not be massive, but when you're looking at 30 million frames, it might be significant. So it's something to keep in mind. And then NumPy arrays, the advantage there is you don't have to do a whole bunch of folders necessarily. One file could represent the entire video. But the disadvantage is it doesn't have compression. So you've got a large footprint. And then at the same time, you can't necessarily load in a single frame from a block of a NumPy array that's been written to disk. You have to load the entire thing all at once. And that might be cumbersome if you choose later on that you want to access it in a different way. And so what I've used a lot in some of these bigger data scenarios is use an HDF5 array, which is kind of a hybrid between a NumPy array and a bunch of other formats. And basically what it allows you to do is keep track of the metadata, the file names, the data, It allows you to chunk it and compress it in various different ways. If you chunk it in the correct fashion, then you can access it very quickly without wasting any read speed. So the big thing with HDF5 is with a typical file, you might have, like with the NumPy array, you have to read the entire thing before you actually get the completed array. But with a chunked HDF5 array, I could chunk it in the shape that every single chunk is one frame of the video, and then I can load in just that frame of video. And on top of that, HDF5 allows you to add in any compression that you want on top of it. And it just has some nice setting dials, so you can chunk it in the way you want, you can compress it in the way you want, and you can access it in the way you want. And it has a little bit of overhead in terms of the file size, but it's highly advantageous in terms of your read speed and your flexibility when you access it. And so this is something that I've been using pretty heavily whenever I interact with video. This has been my second time working on a project with video. And so understanding what that project looks like, taking 500 gigs of compressed MP4s, they've got about 300 frames each. It's 1920 by 1080 by 3. And then after 30, 60 hours of running, I've turned the entire thing into a 300 gigabyte HDF5 array. And I was only pulling basically every 10th frame. Just in order to reduce the amount of data, because the HDF5 has compression, but it's not necessarily MP4 compression that can be very efficient across keeping the continuity of frames and all of that stuff. And then it's also reducing down to 300 by 300 by 3, just the faces instead of the full frames. And so after doing that, I was able to train just the simplest model possible, ResNet 18, out of the Torch Vision package. And that got me up to first pretty quickly. So that was, I just have this weird thing where if a competition comes up that I'm interested in, I'll typically blitz it and try to get a good score as fast as possible. And so I got a pretty decent score right off the bat, and I was able to keep that for about a month, actually, because I just prototyped out a solution so quickly. But then later on, people caught up and surpassed me as they devoted more time to it. And so the gist of this solution is I'm looking at individual frames like I was talking about. So I just look at one frame and I say, did this come from a video that was real or fake? And it just learns that over time. And since we had this imbalanced problem where we have one real and then we have 5+ fakes for every single one, I needed to balance that in some way. And so what I did was undersampling. So for every one real video it saw one fake. And so every epoch it would go through that process. Instead of seeing just the standard sampling, it would be way too skewed towards the fakes. And so one of the things that was important in this was, since we were using log loss, which penalized very heavily for when you're confident and you're wrong, I started using soft labels. So typically you might say, okay, if it's real, mark it as 0. If it's fake, mark it a 1. What I started doing was I would use 0.05 if it's real and 0.95 if it's fake. And so my model wouldn't output overly confident answers, and it would learn to just be a little bit more conservative with its estimates. And so that's the entire solution that got me to first for a while. And then looking on how I could improve on that, I noticed that there were big issues in validation. And so that's always important for a Kaggle competition, is trying to figure out, how do I measure the performance of my model and make sure that the improvement that I'm making is actually indicative of the performance on unseen data. And so the problem that I was seeing was that it might devolve into a face identifier. And so the data only had about 200 faces, we figure. And so if there were faces that were only in the real set and not in the fake set, or vice versa, then it might say, oh, I've seen this face for Paul. Every time I see the face for Paul, I know real. And every time I see the face of Sally, I know it's fake. And so it just learns the characteristics of these two different people rather than learning, oh, this person was grafted onto this other person. And so figuring out that process and making it so it works on unseen faces rather than just kind of memorizing the two sets was one of the problems that I wanted to tackle. And that's pretty difficult for us to do because we weren't necessarily given labels of what actor was in which video. So some people did a big effort trying to figure out, can we just group these up and figure out who's in what video, and can we set up a validation set that has unseen actors and stuff like that. But ultimately, I don't think anyone had much success with that. And so the next step of taking it further was figuring out, I kind of looked at it as a hacking problem where someone has generated something with this process. Is there something in this process that I can attack and kind of exploit some weakness that they have? And so one of them was the discontinuities between frames. And so that was something that came up in the questions earlier. And basically, if you look at that deepfake process, there's nothing that enforces that it has continuity. So you might have, it looks, the face looks a certain way on one frame, and then the next frame it looks entirely different. There's nothing that's actually enforcing that to be similar between different frames. And so I thought that that was probably one of the different attack vectors that I could look at. And so all throughout this process, I'm reading a bunch of papers because there's been lots of research that's done on these deep fakes. And so one of the papers was showing that you might even be able to just address the rotation, the transform that was done, or the blurring, or the histogram equalization, or some other process in the pipeline might be trivial to detect. And if you could detect that, then you don't actually have to care about whether it was a generated face or not. You just have to care if it was blurred in some way, and you can easily make that trigger some concern. And then the other thing that I was looking at was there are all of these pre-trained models that essentially extract embeddings that tell you who a person is. And so this is the kind of stuff that's in a lot of smartphones and laptops and stuff like that now, where you can just walk up to it and it knows what you look like, and so it will unlock for you. And so this Face ID technology basically generates these embeddings that are similar to what is done in the autoencoder, and it will basically define someone's identity. And if you can look at that across all of the frames of video and you see, oh, it's Paul, 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 George, and then it goes back to Paul, you can say, oh, looks like a deep fake was here because the identity randomly changed. And then the other attack vector was the audio. And so one of the early things I did was just look at the comparison of the real video and the fake video's audio, and I found that about 8% were altered. Is there evidence that showing some of the region around the face is valuable to the model, not just cropping the face? Yes. So that was something a lot of people were discussing in the discussion forums after the competition closed. And so it's pretty important to look at the surrounding area and understand if there might be an alteration in resolution or something like that. And so a lot of people were noticing that if you increased, they're calling it the face margin, basically. So if you have this region that captures the face, then you just do slightly wider than that, and you're able to capture the surrounding context too. And so on the topic of the temporal information, I've done various video-based projects in the past, so I kind of just pulled out my bag of tricks, one of them being frame differencing. So if you take frame 1 and then you subtract it from frame 2, then you'll see what the difference was between the two. And if we expect that the face typically doesn't change very much, then a deepfake would probably trigger that if all of a sudden it changed identities or it doesn't have the same level of continuity that we expect. And so this bottom left picture is showing the frame differencing moves basically all of the static information, just tells you what the difference was. And so that's useful just because it can show movement, but also because it eliminates all of the unnecessary background noise. So all of the information that is static, your model doesn't have to sort through that and say, what is the significant piece? Because all of that stuff is just gone. And then the other one is optical flow. And so this is a similar technique that basically just tells you where the motion is going. And so both of these techniques are pretty useful. In the past, I've used these for a self-driving car thing, where basically it makes it a much more dense representation of what you're trying to learn if you care about the motion rather than the actual raw color values of all of the different stuff. And then the other thing is you can just use the raw color information and then pass that into a CNN or something like that, and then pass all of those frames that have passed through the CNN into the LSTM or GRU or the various different neural network types that you have. And so there's also 3D convolution. So instead of just iterating or convolving across a flat image, you can also convolve across frames. And so there's various different techniques that have been developed that can handle videos in that way. And so in terms of detecting the post-processing, there's this paper that popped up that basically showed we can generate something that is like a fake, but isn't necessarily a fake, where we just take the face, we do the transform we expect to happen in the process, and then we can undo the process and we can do all of the blurring and histogram equalization and all of that stuff. And so it's the same face grafted onto the same person, but it's had that entire process happen to it. And so if you could just detect something has changed here, then you can get a very general detection of the fakes. And then this is detecting the changes in the face ID. I already kind of talked about this a little bit. There's pre-trained networks that will basically output this is what this person looks like. And then if you see that rapidly changes over a short period, then you know that something's probably been altered. And so I looked at various different ways that I could fuse this information along with the raw image that I was looking at. And then also looking at the audio, I looked at previous competitions and what people had done on audio competitions, and I found that a lot of people were turning the raw waveform, this top right graphic, into spectrograms, which is this bottom right graphic, and they were having really good success with basically treating audio as an image once you turned it into the spectrogram. So I spent some time and I turned all of the audio bits out of the video into spectrograms, and then I trained various models trying to utilize that. But I don't think anyone really had any success with that. Looking at the data, only 8% were altered in any way, so they weren't exact copies of the original. And then listening side by side with one version of audio and the other, we saw that they were, to the human ear, you couldn't even hear a difference in almost any case, even in the ones that had been the most altered of any of them. So it might not have even been the intent for them to have fake audio in this competition. It might have just been compression issues or something like that, issues in the file. So one of the things that I kind of got caught up in and chewed up like a month of my time was this. I don't know how they would say it, but I would call it CoVR, which is this compressed video action recognition. And basically, the idea here is if you just entirely skip the process of decoding the MP4 and you just train a model directly on the compressed video still, then it's probably a denser representation of the information. And it's also going to save you a whole bunch of time on the um, decompressing. Um, and so I don't really know a ton about the details of MP4 compression, but my understanding is that there's various different kinds of frames. And so iframes are kind of the building blocks of the rest of the frame. So you set an iframe, and then you might have P frames and R frames and various other things that are capturing the motion and then some corrections in video and stuff like that. And it's this really clever way of minimizing the amount of redundant information that you're sharing. And so that's why you're able to store these long videos that are only 2 GB or something like that. You can store a whole movie and it doesn't even fill up your hard drive. And then if you try to decompress it, it ends up being this massive file. And so the idea in this paper was basically we can take this compressed representation, train a model on top of it, and it turns out it's in some cases even better. Had a question about what is a CNN. So I mentioned that on an earlier slide, a convolutional neural network. Basically, the idea behind that is it's a neural network that a lot of people use for images, and the advantage it has is it's looking at the spatially related pixels. So in a lot of models, it might not care what order things are in. So if you're predicting house price or something like that, and you have a whole bunch of variables, you could shuffle those variables and it still means the same thing as long as it's consistent throughout your model. But if you do that with a video, the video no longer makes sense no matter what you do with it, because the pixels that matter, the pixels that make up someone's eye and someone's nose and stuff like that, is no longer close to each other. And so that's what the CNN utilizes when it trains is the spatially related pixels. And so in terms of analysis, looking at what worked and what didn't work, what did start working for me was sequential models that actually cared about the series of frames. And so that was taking a CNN, and that would basically create that embedding of size 128 or whatever I defined, and then pass that to an LSTM. So it creates an embedding for every single frame, and then it passes it to an LSTM, and it iterates over all of those, and it learns across the sequence, fake or real, basically. And then a lot of image augmentations that people were using, I started using those, and those were helpful. So there's this package called Albumentations, and that has various simple things, like if you just want a horizontal flip, if you want to do JPEG compression, if you want to change the brightness, if you want to do various things like that. And that seemed to be pretty helpful. And a lot of people in Top Solutions wrote about how they did very interesting image augmentations there. Does Albummentation support video frames? Not directly, but you can pass it individual frames. I had to do that with a for loop. I don't think there's any way that you can pass it just like a full array of video frames. And then, like in every other competition, ensembling ends up playing a big part. So I trained a bunch of small models, a bunch of ResNet 18s, a few of the LSTM models, and a few that were cropped at a different distance or at a different size. So some of them were at 300, some of them were at 224. I took all of those models and I ensembled them and then got a decent result out of them. The soft labels were helpful. I think almost everyone did that in some way because the videos we were predicting on are not necessarily the same as the videos that we're training and validating on. So that's for the public leaderboard. We had a set that we think is somewhat similar to what we trained on. And then on the private leaderboard, which still isn't going to be revealed for another 3 weeks or so, it's being graded on raw YouTube videos and stuff like that. So that's going to be the real test in terms of were our predictions overconfident? Are we going to generalize? And how is that going to work out? We don't know yet. There might be a massive shakeup incoming. We don't know. And so what didn't work, the co-VR thing, that used some pretty specific FFmpeg build, and it had some custom C++, and I just couldn't figure out how to get it to run in the Kaggle kernel. I probably could if I spent more time on it, but there was a certain point where it was like, I just want to go back to actually working on this problem and not just software debugging and fiddling around with C++ that I don't know very much about. And then the audio detection didn't work. The face embeddings, I had that included in some of my models. I'm pretty confident it wasn't actually doing anything. But at a certain point, I had trained the models and I already had them in there, and I wasn't going to retrain the models without, because that was just going to take too much time. So I had models at the end that use the face embeddings, but I'm pretty sure they didn't matter. And then I tried samples with the optical flow and frame differencing, and for whatever reason, I wasn't able to get any signal out of them. So it would just basically be stuck on raw random guessing basically the whole time. And then the other thing was detecting the post-processing. So what were the prediction runtime constraints? So we were predicting on 4,000 videos, and we were given 9 hours to do that. And a lot of people found that pretty difficult to do. If you wanted to just actually decode the full MP4 for all of those, unless you did some fancy tricks, you probably didn't even have enough time to do that. So pretty much everyone was relying on doing some sort of sampling of the frame. So most people might do every 10 frames, they pull one or something like that. And the big slowdown there was you had to decode the video, but then you also had to do all of the frame detection or the face detection models on top of that. And so that slowed things down quite a bit unless you organized it in exactly the right way. Under those constraints, you found it better to ensemble small models rather than train fewer larger models. So the other constraint there is we only had 1 gigabyte of external data we could include, which included our models. So if you chose to do a very large model or something like that, then you could probably only do a few of them. And the way I structured things, I was just doing ResNet 18 and the smaller models and stuff like that because I wanted to iterate fast and do a lot of experiments. And it didn't seem like there was a strong correlation with going up to the larger sizes and getting more performance out of it. Primarily because it was difficult to gauge when you started overfitting or when you were just starting to fit on noise and stuff like that. So yeah, we were playing in a pretty tight sandbox, and I think that there were a lot of things that were kind of limited out of existing just because we were given not a very big system. We didn't have very much memory. We had a single GPU. But I guess that's realistic for a scenario in real life when that would be deployed somewhere. and examples of deep fakes versus not, yeah, we'll look at a few of those in a little bit. So error analysis is something that I always spend a lot of time on. So trying to figure out what is going wrong with my model, which ones is it getting wrong, why is it getting them wrong. This is a fairly complex pipeline, and so looking at that and saying, is it because I'm not detecting the right face? Is it because it's getting cropped out? Is it because I'm just not storing it properly? Am I not loading it properly? There's all kinds of different things that can go wrong there. And so what I do is I just look at the ones that have the highest loss. So looking at this histogram down here, we can see that there's a whole ton of these videos that my loss is really low on. That means that the prediction is fairly good on it. And then we have this long tail that goes all the way down to or up to a loss of 3, which means that this one I got wrong and it was very confident on, and that one got a large multiple of all of the loss of these ones. And so looking at those and understanding, why am I getting that one wrong? Can I eliminate that in some way? Can I make it less confident, or can I get that correct? Is pretty important for minimizing your score on the leaderboard. And so looking at that, I saw that one of the most common problems, one of the characteristics of videos that I was getting incorrect was ones where they were looking side on when we had a profile view of them. And so I did that by looking at a whole slew of like the top 100 basically videos. And I took notes of basically various characteristics. So is it a profile video? Are there multiple people in that video? Is it too dark to really see the person? And then after I categorized all of those things, I saw, okay, about 45 out of 100 of them have profile videos where the person is looking side on. And then the other major problem was when there were 2 people in the video. So there were times where people were having a conversation back and forth. And so the face detection might pull out both of the videos, but the way I had stored them, it actually just kind of interpolated them. So it would see one face, then the next face, then the next face, then the next face, rather than having them as 2 separate streams and understanding this is continuous in some way. And that was something that I never necessarily addressed, but other people at the top of the leaderboard did. And so you can see side-on faces, and then this one where their deepfake process actually put a face just randomly in the sky, and then my face detection process found that face in the sky. And so I was doing a prediction on that, and somehow it determined that that was still real in some way. So I just thought that was a funny error that it came across. Does face detection work better if the exposure is increased? So that is something that a lot of people were trying, is basically maybe the video is too dark, so let's increase the brightness or something like that. And that did seem to work for some people. That's not necessarily something I really tried. It seemed like for the most part, the face detection algorithms were pretty good out of the box. Even in the case where it was a super dark setting, they still seemed to be able to retrieve where the face was in the frame. And then after that, I was looking at the frame level difference. So comparing the real video and the fake video, and just kind of taking the difference between the two and saying, where is the most significant frame difference, and seeing what that looked like, and seeing one of the things that I was specifically looking for was these were MP4 compressed, so it's not necessarily a perfect match. So I knew there was going to be a certain amount of noise between the two, but I wanted to see if there was some easy way to see, oh, okay, now there's a random spike and this face is just significantly different from the one before. And so I made this graph, which is basically showing the average pixel level difference between the two is typically around a range of like 2. So these are RGB values that go from 0 to 255, and so if they're only different, if they only differ by 2, then that's not really that big of a deal. But if we look over here where they're differing by 8, that's actually probably a pretty significant difference. And so we can see that at this maximum point, the real video looks like this, and the fake video looks like this completely blurry mess. And for whatever reason, my model looking at this was one of the higher loss ones, did not determine that this was fake. And so that's something that you kind of have to scratch your head and you have to go, okay, why is it not understanding that this is fake for some reason? And that was something that kind of clued me in. And maybe it's just memorizing the faces, because this is clearly blurred and destroyed in some way. You would think that it would be able to discover that. And so my preliminary result ended up 216th on the leaderboard. 6 hours before deadline, I got a submission in that pushed me just a little bit forward to be in the bronze zone. We'll see if that stands on the private leaderboard when they run it on the new data. Fingers crossed that it does. But yeah, that was how I fared after spending some time early on and then kind of burning myself out and not putting much more effort into it at the end. So reflecting on what I could have done better, I think that this is always an important step to figure out, okay, how could I be more efficient next time? What could I have done better? Why did I not get first, basically? What did other people know that I didn't? Was it something in the process? Did they have more compute power than me? How do you propel yourself to be the best at whatever you're doing? And I think that one of my critical errors was that I needed to prototype smaller. And so I was prototyping relatively small in the sense that I was only sampling some of the frames and I was only applying ResNet 18, but I still think that I probably could have been doing smaller trials, because these trials were still ending up 6 hours at times. And then just the data prep process, if I wanted to redo something, that 30 to 60 hour process, I did that with the optical flow and the frame differencing and the various other things, and running it across the entire data and leaving my computer to run for 3 days or something, and then coming back and seeing, oh, the optical flow sucks. It got me a basically random guessing score. I needed to figure out a way to do smaller trials and get feedback earlier rather than wasting days at times on these experiments. What compute power did I use? So I have a old, decrepit at this point, Dell T7600, and it's still fairly powerful. It's got dual 8-core processors, and I also have dual GPUs in there, so I'm pretty well equipped, actually. And for this competition, I bought an 8 terabyte hard drive so I could fit all of the video in the various different formats that I wanted. I'm pretty well equipped in that regard compared to most people, but the people in this competition, some of them were at research labs and stuff like that, and they had full DGX 100s with 8 GPUs and stuff like that. So the 2 GPUs I have are the 1080 Ti's, and so I got those a while ago when they were really cheap for only like $400 a piece. And I think they're still probably the best value card right now if you can get them for that cheap. Had good experience with them. There's new faster cards at this point, but bang for your buck, I think those are pretty good ones. Going back to reflecting on what I could have done better, I think that I really just needed to throw more stuff out there. So looking at what some of the top people did, it was all stuff that I had in my tool belt, but I just didn't pull out and use. So like the 3D CNNs, I never tried that. I never really did a lot of the things that the top people did. And I don't really have an explanation of why. I just kind of got caught up in doing the little experiments that I was doing and not drastically changing what I was doing and trying big changes, which I think is what you need to do in these competitions. Sometimes you need to kind of break from the typical wisdom and just try something a little bit crazy. And so I already talked a little bit. I spent a lot of time on stuff that just was not really significant. And then the other thing is I've found that as I've spent more time in the field, I'm a little bit, I hold on to the things that I used a while ago, and I need to kind of just go with whatever the state of the art is. So I still use Atom Optimizer and various other techniques that have been kind of surpassed recently, but I've just kind of said, oh, this is good enough for now. So a lot of the things were various augmentation tricks. So I just did the simple, here's a horizontal flip, here's some JPEG compression, but a lot of people did some of the more state-of-the-art cut mix and various other variations on that. And I kind of just stay away from that because I feel like those are just small improvements that don't really make a difference. But I think that those things kind of add up, and I need to kind of just embrace whatever is the best thing right now, even if it is just a 1% gain or something like that, because those things add up. So looking at the second place solution that the guy shared, one of the things that he said was very important was using a large face margin. So that was one of the things that we talked about. You have this region is the face, and then you go much wider and you look at the context beyond that. And that was something that I was doing to a certain degree, where I would just pad it by 10 pixels. But what they were doing was they were actually looking at the face and then padding based off of the size of the face. So if the face was 100 pixels wide, then they would look 0.5 to the left, 0.5 to the right. So that would be 50 pixels to the left and 50 pixels to the right. And so they were calling that face margin, and they were expanding it beyond the zone of just the face. And I think that that additional context is probably important, but not necessarily crucial. And so the other thing that they looked at was using much higher capacity models than what I was using. I was using ResNet 18. So if you look at ResNet 34 over here with 20 million parameters, I was below that. I was like over here. And they're all the way over here using 60 million plus parameters. And that was stuff that I kind of shied away from because in early experiments, it didn't seem like bigger networks really mattered. But I think that maybe that was just early experimental error, and maybe I should have spent more time on that. Looking at these higher capacity models, it starts to become an issue of just GPU capacity. You start running out of memory space on the GPUs. And I didn't really have any massive problems with that, but I figured I would, which is why I stayed with the ResNet 18s for a while. The thing that I think was particularly exceptional about this solution, beyond all of the other points, was that they did multitask training. So what I was doing was simple, is this video fake or real? What they added into the mix was, we have the original, we have the fake. Let's take the comparison of the two and see which pixels are significantly different. So on that previous table, you might see, oh, this pixel is more than 10 values off from the other one. And so their model would try to predict which pixels have been altered. And that additional supervision is probably the most significant thing that they contributed. I think that that's probably how they ended up in second, because I think that these are important, but not as important to get you up into second as this. And I'm a little bit kicking myself for not figuring that one out, because the previous like 3 or so competitions I've done have been segmentation competitions. So I know that you guys had Alexi present the clouds competition. I did that one a while ago, and I ended up getting 24th. So I'm pretty well versed in that kind of problem, and I just didn't think of it in that way, and so I wasn't able to pull that trick out of my hat. If I did, I probably would have done much better. Did anyone use the pixel co-occurrence matrices of the images rather than the images themselves, or looking at their Fourier transforms? Not that I know of. I didn't see anything like that, so I can't necessarily speak to that. And then the other solution that was shared that was high up on the leaderboard, this competition only closed a day or two ago, so a lot of people haven't shared their solutions yet, and we still don't know how it finally pans out. So some people are probably waiting to see that before they share their solution. What these people did was pretty interesting, though. In my approach, I'm looking at each frame. I extract the face, and then I extract the face at a different spot in the next frame, and the next frame, and the next frame. And it's this bounding box that is moving all over the place. What they chose to do is they found the bounding boxes for every single face, and then they said, let's find the biggest area or the smallest area that encapsulates all of the area that the face ran through. And then let's just chunk out that entire box. And so where mine might have taken a 224 region, theirs might take a 400 by 400 region, but it captures all of the context that the face ever passed through. And they were, in doing that, they were able to keep it as one continuous box of video, essentially. And they were able to keep it as a single MP4 stream and then re-encode it as an MP4. And so with that clever trick, they were able to take it from 500 gigs down to, they said, 17 gigs, which is just really impressive that they were able to condense it down so much and just extract the areas of interest for the face. And then on top of that, they did the 3D CNNs that we had talked about, where it's not just convolving over the single frame, it's also convolving over the different frames. And they seem to have really good performance out of that. They got all the way up to 20th. And interestingly enough, they said that segmentation didn't work for them, whereas the person in second said that that was one of their crucial tricks. Kind of interesting how people can go through entirely different pipelines, end up with good solutions, and then disagree on what is a good way to approach the problem. So these people, they made this graphic and they showed that they're doing their 3D pipeline, and then they also do the 2D pipeline, which is more like what I had been doing. And then they had various different variations of these 3D models. And that's all I have.
Sorry, I needed to unmute myself. Can I ask you a question?
Yeah.
Earlier, you alluded to these serious concerns about, let's say, train, val, and test, right? That we're worried that that certain people are only in real videos, or they're only in fake videos, and there's certainly lots of people who are only in the training data, and therefore in the training and validation data, and of course in the test data, maybe none of those people. That seems massive, massively important. And did anyone say what they? Okay, first of all, do you have any measurements of that effect? Did anyone try to determine, if there are some of these mysterious people who only show up in certain contexts, and what kind of strategies did people employ?
One of the things that people were trying was the videos were split up into 50 different folders. And so it turned out that the split was not necessarily random between the 50 folders. And so what people started doing is they would do they're split based off of the different folders. So they would take the first 40 to train on and then take the last 10 to validate on. And that seemed to be good enough for most people, even though there was overlap between the various folders, because it did somewhat separate those groups. The other thing was the last 10 folders was the only set of folders that had audio alterations. So it was never explained to us what the difference between these different folders are. Some people hypothesized that it was an entirely different deepfake method, because there were they said that 3 different methods were used. We don't know exactly which ones. I can kind of assume that it was the top 3. I know that the one we looked at, Face Swap, that's the top one, and then there's Deep Face Labs, which is the second most popular, and then some other third one I'm not aware of. But lining up the validation, a lot of people tried interesting stuff with that, and I don't know that anyone necessarily solved it. So I think it's going to be interesting to see what happens on the private leaderboard when we get shown totally new videos from YouTube and stuff like that. I think that might totally throw everything off.
Do you have any thoughts about what methods might be more resilient to that shakeup? I certainly don't, but maybe you do.
If I knew, I would have done them. So I think that what was valuable that some people did is they used those face embedding systems, and they were able to cluster the faces together. And so they were able to say, oh, it looks like these videos all go together, these videos all go together, and they all feature the same person. And then after the fact, they were able to do a split based on that. And so they could say, okay, these 150 faces go into train, these 50 faces go into validation, and then you can work from there. But of the people who have published their top solutions, no one has mentioned anything special about a validation scheme. So I don't know, maybe that's not that valuable. Maybe we'll see something entirely crazy happen on the private leaderboard though.
Yeah, I mean, if you do something about this now, you're probably hurting your public leaderboard score, right?
Mm-hmm. Yeah.
So those are the sleeper solutions that are going to shine. And also, of course, it's one thing to create the cross-validation regime, right? So we're actually properly measuring our performance. Mm-hmm. But also, it would be nice to do something about this bias in the data, right?
Yeah.
And so that's like a completely different set of issues. Go ahead.
One of the things that I was struggling with was, do I choose that folder validation or do I do just based off of video? So making sure that I don't have all of the fakes on one side of train or val or something like that. And so doing it just based off of video and not necessarily by folder, I was able to get my validation loss results down to like 0.08 and ridiculous stuff like that. Whereas the top solutions in the competition were like 0.2. So there was just some form of leakage there that needed to be fought in some way. And some people think that they were able to solve it, but I'm not entirely convinced. So like in the top solutions, they all mentioned very strong augmentation techniques that cause them to have correlation between their board, but I'm just not convinced that it was from a good validation scheme. I think that they might have just had augmentation that was so strong that it was essentially destroying some of the videos and making it look like they were lined up in numbers, but not necessarily in methodology.
Right. Yeah. If you augment hard enough, you make the problem too hard and you make your model worse.
Yeah.
Okay, well, I stole the last couple of questions there. Thank you very much. I don't know, did we decide how we were going to do applause here? Are we going to say, okay, everyone, you've got 10 seconds to unmute yourself, like 10, 9, 8. It's the button in the bottom left on my computer, at least. 6, 5, 4, 3, 2, 1. Applause! Yay! It was a huge success.